roufaida souakri.
Oui.
تفضلي مرحبا.
In the first, I would like to start by thanking all the responsibles of this event. Thank you for the good organization. I'm so glad for being a part from this first international workshop. I present myself, souakri roufaida, PhD student at the University of Science and Technology Houari Boumediene. The title of my presentation is as follow. Modeling periodic integer value time series with a periodic generalized Poisson integer autoregressive model of order 1. I start by introduction to give an idea about my subject. The non-negative integer value time series of counts are still continue to attract attention of researchers because of their wide usefulness in several practical fields. As example, we have in medicine we have the number of cases of Campylobacteriosis infections time series studied by Freeland and more recently by Wiznani and Bantarzi. We have also in sociology the number of people employed in the short-term disability benefits studied by Monteiro. We have also other fields, the criminology field and financial one. So modeling and analyzing this series remains one of the most challenging area of time series. However, during the last decades, this area knew great developments because of the efforts that have been given to the modeling and studying of the probabilistic and statistical properties of linear and also non-linear non-negative integer value time series models. We have several researchers have proposed integer value time series models, linear and also non-linear, Al-Osh and Al-Zaid. We have Jean and Juan and Yuan. We have also Monteiro, and for non-linear we have Freeland. We have also Bantarzi and Bantarzi, and there are many others. So issues such as inference and forecasting for Poisson time series models have been discussed. However, in practice, our distribution, the Poisson distribution, it is not always suitable for modeling because it is characterized by the property of equidispersion, which means when the mean is equal to the variance. So if we have one commonly observes under-dispersed or over-dispersed counts, which means the mean is smaller or greater than the variance, our process, the Poisson distribution, should not be applied. In such cases, there are several alternative models. We have the one of Bourguignon proposed two marginal distribution, the DP distribution, the double Poisson distribution, and the generalized Poisson distribution. The elaboration of integer valued autoregressive PGPINAR models had not changed the fact that there are many count time series in various fields as economics, financial and medical exhibit a periodic feature. So we have the integer feature and we have also the periodic feature. What does it mean by the periodic feature? We meant that in their autocovariance structure. So we have as examples the number of cases of Campylobacteriosis infection time series. We have also the monthly count of claims of short-term disability benefits studied by Freeland, Zhou and Zhou, and recently Saidon and Bantarzi. So this periodic feature cannot be accounted by the standard integer valued modeling. So the periodic in-time coefficient models are very adequate for modeling this periodically correlated process. So we propose a first-order periodic integer valued autoregressive PGPINAR1 with generalized Poisson marginal distribution. Our new model can fit the data with the periodically correlated structure and also handle the over-dispersed, equidispersed and under-dispersed situations. our plan is like the following. We give some definitions and main assumption. First about the PINAR model with generalized Poisson innovation, and then about the periodic generalized Poisson distribution. We gave the periodic stationarity condition. Next, we gave the form of the autocovariance structure. In part 2, we will talk about the three estimation methods that we used, and we will present some simulation results. So, we start by the definition of our model. Here, our model, we said that instance of Gladyshev, that's our periodically correlated with the period large S is satisfying a periodic first order integer valued autoregressive PGPINAR1 model if it is a solution of the following linear stochastic difference equation, with epsilon t is a sequence of uncorrelated non-negative integer valued random variables with a periodic mean and periodic variance. And we have also this Fenian operator is the Fenian operator of Stoutel and Van Haar operator. And we have also that our process is a periodic generalized Poisson distribution. Next, we present the periodic generalized Poisson distribution. A stochastic process epsilon t is said to have a periodic generalized Poisson distribution if its probability mass function is given as follows. This is the probability mass function. Here we present some properties of a time invariant generalized Poisson distribution. Here we have the mean, the variance, and the index of dispersion. Here we gave the condition, the periodic stationarity condition. So our process xt is a second order periodically stationary integer valued process xt if and only if the unconditional mean and the unconditional variance is given by this formula. This is our obtained formula. Next, we gave the form of the autocovariance structure. Here is the variance. When h equal to 0, we have the variance formula. And when h is larger or equal to 1, we have this formula. In this part, we present the three methods of estimation. We have the Yule-Walker estimation, the conditional least square estimation, and the conditional maximum likelihood estimation. And we compared between these three methods in terms of empirical mean and root mean square. Here we have the formula of the estimator of Yule-Walker. This is the formula. And next, we have the formula of the estimators of conditional least square. Here, formula. And for the conditional maximum likelihood, we have the conditional likelihood function. This is our function. This is our function. This is our function. To obtain our estimator, we must maximize this quantity. Here we present some simulation results. Here we have the true parameter values. Here the true methods, and here we have the estimated value for each method of estimation. And between brackets we have the RMS error, the root mean square error, the table 2, the table 3, and in the end, it's clearly that the CML estimator, the conditional maximum likelihood estimator, have the best performance on mean and root mean square compared with the other two methods. The superiority of the CML was expected because in the estimation we used the whole information of the distribution. The same scenario happened for the estimator of the parameters beta S. However, for the parameters lambda S, the Walker and CRS estimator have the best performance. So, as a conclusion, we have we obtained the following results. The empirical means of the estimator obtained close to the true values, and the RMS decrease as our sample size increases. Thus, the property of consistency is met. Thank you for your attention.
Merci.